Oh. Well, I got 3 people here, and none of you are Kyle. Kyle is always the first one here. What the heck? Well, kudos to all of you. Regardless, he'll be able to watch this video later and be upset that he wasn't the first one here. But she's gonna roll in like a minute or two. Anyway, I'm gonna get started in a minute. I'm just gonna give people an opportunity to kind of get in. Yeah, I'm disappointed too. But I'm going to put a link to what you could potentially use as where is it? As a graphing calculator if you do not have one. And boom. There we go. So if you don't have a graphing calculator, you could always use desmos.com/calculator and type in the function that we're going to, or the functions that we're going to be practicing with today. Obviously, as you can tell by the title, this is Graphing Rational Functions Practice. I did the main lesson on this the other day, and we will eventually be assessed on this information. But I just wanted to get in some practice because I know it was a lot of information to kind of a lot of information to go over in the previous video. So I want to review, refresh, and then get some practice going. So make sure you click that like button, as Kyle likes to say, and make sure you've subscribed and rung that bell. Oh, there we go. Oh, goodness gracious. Matt, are you familiar with the concept of Schrodinger's cat? I don't know if you are or you're not. Of what? Schrodinger's cat. Schrodinger's cat was this concept. It was more of a mental exercise where imagine a box with a cat on the inside of that box, and also on the inside of that box with the cat was a vial of poison. And well, you close the box, and ultimately, the cat, you don't know when that cat's going to get into that vial of poison. You don't know when it will happen or if it will happen. But it's always a possibility as long as the box is closed. So, in an abstract way, the cat is both alive and dead at the same time. And you will not know the answer to the question as to the quality or the stasis of the cat until that box is opened. Thus, cat in the box. Anywho. All right. Let me get some paper. And we're going to get started. Just going to make sure I get the right one. There we go. So I want to recap with you what is expected of you in regards to graphing these particular functions. And then I want to go ahead and actually get that done. I don't know. I'm not Kyle's keeper. Kyle has been here for every live stream for every class. Like, legitimately. He's here for AP Stat. He's here for discrete math. He's here when I just randomly do, like, a silly one. I don't know. I'm not Kyle's keeper. But let's get moving with this. So, to recap. Graph rational functions. The process that you would have to follow in order to get this particular thing done. There are two types of rational functions that we're going to be dealing with. Some are the basic ones and some of the non-basic ones. And I will be sure to recap the two of them with you before each example. And I'll do y, I'll do f of x. But the basic one, I'll write the word basic over here. The basic one is when it looks something along the lines of this. The basic rational function is one where you literally just have a linear function in the bottom of the fraction. And there could be a number being added or subtracted to the fraction. It doesn't have to be there, but it could be there. And ultimately, the value of k, y equals k, would give you your horizontal asymptote. The value of k would give you your horizontal asymptote. In order to get your vertical asymptote, you would have to take x minus h, set it equal to 0, and solve. Now, it may not be x minus h exactly. There may be some other numbers involved, but ultimately, to get the vertical asymptote, as it will be for this entire process, you need to get the bottom of your fraction equal to 0, and then you solve. Create a table of values, and then you kind of go from there, and you graph that whole thing out. But for these rational functions, you need to identify your asymptotes, you need to get a table of values, and then you need to graph this thing out. And I'm going to show you several examples like that. For your non-basic rational functions, they will look something along the lines of this. And I want to use the same letters that I did last time. I'm just looking at my notes. Just want to make sure I get the same ones. Yeah, I used a and b. So I did a of x over b of x. Ultimately, for your non-basic ones, you want to make sure they're written as a single fraction. If they're not, we can make them look like a single fraction. In fact, I'm actually going to make one of the basic ones look that way for a future example. We'll get there. But ultimately, you need to simplify, if possible. I'm shortening my notes here, but you need to simplify if possible, which may include factoring. You can identify any holes if there was something that was simplified, and we'll go over examples like that. Determine your vertical asymptote by taking the denominator, setting it equal to 0, and solving. You can find your horizontal asymptote by doing y equaling the lead terms over the lead terms and simplifying. And I will go over various examples like that. You could also, if need be, find an x-intercept by taking the numerator and setting it equal to 0 and solving. It's a lot of extra little things. I put leady for some reason. Not sure why. It's a lot of little extra things, but this is the basic recap that I did in the lesson from the other day. If you want the full lesson, if you want the detailed explanation as to these steps, please review that other video. But for now, I want to use what we did last time, and I want to put that towards some practice problems. So that's exactly what we're going to do here. Now, again, if you have a graphing calculator, you can take a look at that. If you have a TI-83, you may end up having some weird stuff happen in your calculator. We'll deal with that. If you have a TI-84 or better, that weird stuff won't happen. Or if you're using Desmos, Desmos is also pretty good. With Desmos, you can easily zoom in and out with various examples. But again, we'll deal with that when the time comes. Let's start with a basic example. Yeah, I'm going to do that one. Okay, I was trying to determine which one I wanted to do. So basic example, and I'm going to label this one as basic. So you can hopefully see the difference between the two. But here is the basic example. 3 over x minus 7 minus 8. You can usually tell it is a basic example when there's just a number in the top of the fraction, and if there's a linear function in the bottom of the fraction. I started this whole thing by doing something along the lines of 1 over x. That was the introduction to this whole thing, 1 over x, where x would be that linear function. This is what we got. Now, one thing you could do, you could type this into Desmos. You could type this into your graphing calculator if need be. Just make sure, I'm going to have to reset this. Boom. Just make sure that you're very careful with how you're typing in the bottom of the fraction. As you will note, as you can see right there, I put the x minus 7 in its own little set of parentheses. Parentheses will save your life. If you decide not to use those parentheses, it will mess up on you. So please be careful. If I were to hit graph, this is what I get. I should get a cord to plug my phone in. What percentage am I at? I'm at 67%. I'll be fine. I hope. Now, this picture doesn't say much. It's way moved over to the side, way moved down. It would be a lot nicer and easier if the window were shifted over. And I can do that in a little bit. But let's just pretend that this is all that we have to work with. Now for the basic functions. First and foremost, you can identify your horizontal asymptote as whatever number is being added or subtracted to the end of the problem. It's exactly the same as exponentials. Exactly the same as exponentials. To get your vertical asymptote, your VA, you're going to want to take the denominator and set it equal to 0 and solve. Now this one's quite simple. X minus 7 equals 0. Solve that. You get x equals positive 7. Again, horizontal. Remember your hoi vux. Horizontal asymptotes are always y equal. Vertical asymptotes are always x equal. Hoi vux. This may be all the information that I really need. Perhaps let me go for a table of values. Now, there is a way to get a table of values in Desmos, but we'll deal with that in the future. Right now, look at all these y values. All these y values are around -8, -8 and change, -9, -11. There's an that may be helpful. See, the thing is, when you create your table of values, you want to get a few ordered pairs to the left of your vertical asymptote and to the right of your vertical asymptote. That's where you really want to center your table of values. Let me do that over here. So a couple of numbers to the left, a couple of numbers to the right. Let's go 5, -9.5, 6, -11. My vertical asymptote is going to be right there at x equals 7, so why bother writing it? 8, -5, 9, -6.5. This is what I suggest that you do when you're graphing these on your own. You don't have to put that dotted line in. I'm just putting it there to indicate that that was where the vertical asymptote actually was. We'll deal with that later. Now I'm going to graph this thing out. Now you want to be careful with how you graph this out, because if I were just to create a regular table of values, that doesn't tell me the whole story. In fact, I know based on what the vertical asymptote is, based on what the horizontal asymptote is, based on where this thing is on my graph, I know that I am going to... Oh, you can't see it. It's a little glare. There we go. Based on where this thing is, I am going to be focusing on this quadrant down here. Fourth quadrant. So, since I'm going to be focusing in on the fourth quadrant, might as well. All right, I'll put some points in. 1, 2, 3, 4, 5, 6, 7, 8. There is my vertical asymptote at x equals 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There is my horizontal asymptote at y equals -8. In fact, if it helps, you can put something in like that. And let's put some ordered pairs in there. We got 1, 2, 3, 4, 5. That's -9.5, which is about right there. And 6, -11, which is about right there. Now, the way that we know that these graphs look, it's going to be curving down forever because it's trying to avoid that vertical asymptote. And it will be flatlining going this way because it's going to follow that end behavior of the horizontal asymptote. It's going to follow that end behavior. For the rest of my points, well, I got to go a little bit farther over here. 8 and -5. 1, 2, 3, 4, 5. And then 9 and -6.5, which is about right there. And again, it's following that curve where it is going to avoid that vertical asymptote. And it is going to flatline going to the right, following that horizontal asymptote. That's what this graph looks like. Identify your asymptotes. Create a table of values. Carefully draw this thing out. Now, my calculator, again, doesn't show the full story, but if I were to change my window up, could I go 10? Yeah, I go 10. Cool. And then I'm going to go from -15 to +1. Let's just see if that does it. No, much better. Now, obviously, my calculator does not have that weird, crazy thing in the middle that the TI-83 calculators would have. Mine's an 84. Mine's more advanced. On Desmos, it shows something kind of like this. You just have to rescale that window a little bit. But this is generally what that thing should look like. It has that horizontal asymptote. It has that vertical asymptote going on. It's fantastic. Oh, I love what these things look like. One equation, two distinct curves. If you were going to do a domain, range is a little weird. We're not really going to focus on range for this, but the domain, it goes left forever, all the way up to the vertical asymptote, but it can't touch that vertical asymptote. So I'm going to have to do a curve there, or a parenthesis, unioned with 7 to infinity. I want you to think about this real quick. I want you to think about the absolute insanity that this curve is doing. Watch very carefully. As you travel along, this graph begins to dip down. Down, 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 down. Now I ask you a rhetorical question. How far down is this graph going? It's going down forever. The closer it gets to x equals 7, the farther down it will go. It will never reach 7. Might be like 6.9, 6.999, 6.9999999. It will never actually reach that 7, and it'll keep going down forever. And you'll never get there because forever is forever. It's infinity. But then something magical happens, where off in the annals of infinity, something it will never reach, it'll be going forever in that direction, poof, it disappears, and the graph reappears up here. Up at like 7.000000001, and then continues on its way. It's like time travel. It's really weird. Ha 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 ha. Let's try another one. I'm going to write another example up here. But then I'm going to have to go get a charger for my phone, because my phone is my webcam, because that's what I'm unfortunately resigned to. There we go. Let's see here. Let's try Oh, that's a good one. Yeah, let's do that one. Example. F of x equals 3 over 2x minus 4. Now, I'm going to go run and get a charger real quick because I need to get the proper cord that can reach my phone. Otherwise, it'll die. Hey, there's my head. Anyway, but what we need to do, and I'm going to give you an opportunity to think about, you need to identify a horizontal asymptote, you need to identify a vertical asymptote, and then we need to create a table of values. I'm going to tell you that this is, again, a basic example. The reason why it is a basic example, focus that camera, there we go. The reason why it's a basic example is because there's just a number in the numerator. There is a linear function in the bottom of the fraction. And yes, technically there should be a number being added or subtracted. There is. The number being added or subtracted is just 0. I'm going to go get that cord. If you have any questions between now and the time that I get back, which should be like roughly 30 seconds, please throw them into the chat. I need to answer whatever questions you have in preparation for whoever's watching this video in the future. BRB. There we go. And there we go. Good. Just needed to be charged because my 67% went all the way down to 53% while I was just talking to you. There we go. Good. And we got no questions. All right. Let's see what this thing does. Where'd my marker go? Did I leave you somewhere? I probably left you. I'll get a new one. There we go. So, first and foremost, for the basic ones, my horizontal asymptote is just going to be whatever number is being added or subtracted to the end of this problem. In this case, it's going to be y equals 0. I don't know why I put that little equal sign there. We'll deal with that later. It's just whatever number is being added or subtracted. In order to find the vertical asymptote, you set the denominator equal to 0 and you solve. Ultimately, if you did this correctly, you should get positive 2. I'm going to create a little table of values here. I'm going to try to center my table of values around that vertical asymptote. Let's see what the calculator is going to do for me here. Let me reset my window. There we go. 3 divided by parentheses 2x minus 4. You can take a sneak peek as to what it would look like. Hopefully you can see that horizontal asymptote at 0 and that vertical asymptote that's been shifted to the right 2 units. If I go to my little table of values here, I'm going to try and focus it around where that vertical asymptote is. 0 and negative 0.75, 1 and negative 1.5. There's the asymptote. 3 and 1.5, 4 and 0.75. Looks about right. Let's graph this thing out. Again, put in your asymptote. Since the horizontal asymptote is right on top of that axis, you don't have to worry too much Since the horizontal asymptote is right on top of that axis, you can just embellish it like that. But my vertical asymptote is at x equals 2. There we go. You could do something like that. Let's plot some of these points. 0 and negative 0.75, 1 and negative 1.5. And you can see what that thing is doing right there. Again, moving to the right, this curve is going to avoid that vertical asymptote. To the left, it's going to flatline and follow that end behavior. 3 and 1.5, and 4 and 0.75. It's going to avoid that vertical asymptote, and it is going to flatline going to the right. This is what your basic rational function is going to look like. The non-basic ones are going to get crazier. I'm going to do a non-basic one in a moment. Again, this is just graphing rational practice. Domain, domain's super easy. Domain, negative infinity up to the vertical asymptote, unioned with the vertical asymptote to infinity. Make sure you put parentheses around the 2's. It's not including the 2. It will never reach 2. It can never reach the value of x equals 2. It would make a 0 in the denominator. These weird things. All right. You guys ready for a more complicated one? You're probably not ready, but I'm going to give it to you anyway. I want to give you a fun one. My version of a fun one. See what I can find here. Oh, those are always lovely. Those are lovely. That could work too. I'll deal with that one later. Okay. Let's do that one. See, at this point, Kyle would be freaking out. Sparky, why would you give us a terrible one? I want to give you a non-basic one. Here's a non-basic example. Now, the non-basic examples are going to get nuts. They're going to get nuts. There's no way of avoiding them, unfortunately. But this is what we have to deal with. Oh, but I want to do that one too. There's so many great examples in this thing. Yeah. Yeah. Let's do that one. Cool. I'll freak out for Kyle. Sure. Here's the example. Oh, do I? No, I'm gonna say I want to save that example, and I want to do this example. Okay, cool. So we'll do this one. It's Kyle with a K. Yeah, probably. Anyway, I had a great example, but then I decided, no, I need to save that one for a little bit. Let's do one like this. Let's do x squared minus x minus 12 divided by... I gotta make sure this number works out the way that I want it to. X squared plus 3x minus 28. That works out for me. I believe that should work out quite nicely for the greatness that I have in mind for you guys. No, Kyle's freaking out is much better than that. But this is a non-basic problem. The way that you can recognize the non-basic problem is by way of the fact that there's no linear function in the bottom. There's no linear function in the bottom. Not only that, you have variables in the top. When you say not that bad, are you referring to your performance of acting like Kyle or the problem? Okay. But let's talk about this. Now I'm looking at this problem. I'm gonna have to identify all those asymptotes. I'm gonna have to see what the table of values looks like. Oh my gosh, this thing is so terrible. But everyone gasp. Kyle's in the chat. Yeah, Rachel's very mad at you. In my timestamps, I'm gonna have to make a note that Kyle showed up. Seriously, Kyle, where is your pass? Oh my. Sure. All right. Multitasking. All right, fine. I'm going to continue with the problem. So I threw this problem up, and there's a lot of things that we could do. There's a lot of things that we should do. But one absolutely imperative thing that you should do with this problem, you need to factor first. You need to factor the problem first. You absolutely have to. If you were to factor this problem, you would get x minus 4, x plus 3 on top of the problem. The x squared minus x minus 12, that's what it factors into. The two magic numbers being negative 4 and positive 3, adding up to negative 1, multiplying to negative 12. On the bottom of the fraction, you end up with x plus 7, x minus 4. Because 7 and negative 4 multiply to negative 28 and add up to negative 3. For those of you in the chat, what do you notice happens after you factor? What is one vitally important thing that happens after you factor? Oh no, I see people dropping out of the chat once I have a question. Okay. Clearly, Rachel has been paying attention to my notes. Yes, there is a hole in the problem. The reason why there is a hole is because of the x minus 4s canceling each other out. Because you had something cancel each other out, you automatically have a hole. Set the x minus 4 equal to 0. You have a hole at positive 4. We're going to have to deal with that later. We will have to deal with that later. Next, you can figure out a vertical asymptote. You don't always have a hole in these problems. You will not always have a hole in these problems. It's only if something cancels after factoring. Vertical asymptote. You set the denominator equal to 0. The only thing left in the denominator is this x plus 7. You get x equals negative 7 as the vertical asymptote. There's only one vertical asymptote in this problem. Oh, yeah, Kyle, I know that. Yeah. What happens is there is a timer, but then like if you close out the quiz or something like that, it actually stops the timer. Yeah, it's fine. It is what it is. Anyway, horizontal asymptote. Now, horizontal asymptotes for this particular problem, for the non-basic problem, you're going to have to take the leading term from the top and bottom of the fraction. You're going to have to take the leading term from the top and bottom of the fraction and set them up in a little fraction and simplify. X squared over x squared just simplifies to positive 1. Because of that, you have a horizontal asymptote at y equals 1. Rachel. You can't force people to do that. See, even I can't see who is in here and who is not in here. The only thing I can do is actually look at the participants. And Kyle, you can't time anyone out unless they actually participate in the chat. So, well, now they do. Anyway, going back to this, I'll review what we just did in a little bit. You could also identify an x-intercept by taking the top of the fraction, the numerator, setting it equal to 0, and solving. You also did that. Now, for this problem, again, I tried to review with you what you needed to do at the very beginning. Number 1, simplify if possible. We can factor, we can simplify, cool. Identify any holes. Well, if anything cancels out, you have a hole. You can identify any vertical asymptotes by taking the denominator and setting it equal to 0 and solving. You could identify a horizontal asymptote by taking the leading terms of the problem, setting them up in a fraction, and simplifying. You get a horizontal asymptote at 1. You can identify any x-intercepts by taking the numerator, the simplified numerator, setting it equal to 0 and solving. We have all of this information. Now we can get a table of values. Again, when you create this table of values, you're going to want some numbers to the left and to the right of your vertical asymptote. Now we do have a hole in here as well, and we'll deal with that hole in a little bit. Let me just double check, make sure I typed this in correctly. Parentheses around the top and the bottom. Good. Let's go to the table of values. I don't want to look at the graph just yet. So I'll look at the table of values. My vertical asymptote is at -7. So there are some numbers that I absolutely do need. Let me put this little table of values over here. Now this table of values may be a little bit more than what I'm used to, only because of that hole. We'll deal with the hole in a little bit. There we go. I understand there are decimals, Kyle. Shut your face. But look, I got no decimals in my table of values. So mirror. But yeah, that's not always a guarantee. What kind of decimals? In the table of values? Those decimals are really not that bad. Whatever. Anyway, these are the numbers surrounding my vertical asymptote. Again, couples to the left, a couple to the right, that's fine. But let's take a look at where the hole occurs. Now, if you notice, for the vertical asymptote, there is an error where the vertical asymptote occurs. There is also going to be an error where the hole occurs. And I'll show you that on the graph in a little bit. Now, it may be important to recognize where that hole is supposed to be. We'll deal with that in a little bit. But perhaps I need to just do something like this. Positive 3.6, positive 5.67. Those are the numbers that are surrounding the hole. Now, you don't know exactly where that hole is occurring. There is a way to do that, but I'm not going to worry about that. But you can determine approximately where that hole is going to be, and I'm going to show you how to identify that on the graph. Now, I'm not going to look at the calculator graph just yet. I just want to graph out my information, and let's see if we can't do this. Now, first, there is a vertical asymptote at -7. Ran out a little room, that's okay. There is a vertical asymptote at -7. And there is a horizontal asymptote at +1. And this part of the graph, I've had to do that a little bit differently. Oh well, I ran out of room. We'll deal with it. We'll figure it out. Now the hole, I'll deal with the hole in a little bit, but there is an x-intercept at -3. There is an x-intercept at -3, and that's quite nice. We could put that ordered pair there if we wanted to. I was just double checking the table of values. So what we can do. -9, +3. It's about right there. -8, +5 is about right there. Now those are the two to the left of the asymptote. The thing will curve up forever, avoiding that vertical asymptote, and it will flatline going to the left. It'll flatline and it'll follow that horizontal asymptote as an end behavior. That's what that graph looks like. You miss going to class, Kyle, mainly because, well, you've been at home for 3 weeks. Oh, goodness. Eventually, you will all go nuts. Whatever, I don't care. Back to this. To the right, I'd be at -6, -3. Be about there. And -5, -1, which is about right there. And you can see what that thing is doing. It's curving to the right. Up and to the right. But keep in mind that you are you're going to flatline going to the right, and there is going to be a hole somewhere around right here. 3 and 5. There we go. You can see the thing flatlining now. There is going to be a hole right at +4. Somewhere in that curve. So let me curve this thing down to the left and then to the right. I'm going to fix this in a little bit. It's going to flatline right there. There is a distinctive hole right there. Boom. There's the hole. This is what our graph looks like. Now, the calculator may not show you this perfectly. Desmos may not show you this perfectly. But there's definitely going to be a hole right at that spot. You have to indicate that with a little open circle. That would be fantastic. Let's see what the calculator says. See how it compares to what I just drew. Nice. Very nice. This is exactly what what I have drawn right here. Pretty much, except for the dotted lines and whatnot. But it's exactly what I have drawn. And look at this. 3. That's a lot of work just to answer a math problem. Can I just have a 79 for the North program here? No. Yeah, Matt, it's a lot of work for a single math problem, but that's the beauty behind this thing. Sometimes the most simple of problems may take forever to solve. I'll talk about that in a minute. I have an anecdote for you in a minute. Let me finish this problem and I'll tell you my anecdote. But now look at this. At 3, I have the value of 0.6. At 5, I have the value of 0.67. Look what happens when I type in a 4. When I type in the 4, nothing happens for the y value. That's where the hole is. So do we have the dotted line, or is it just for reference? Hold on, a couple things. I want to address Rachel's statement, and then I want to address Matt's statement, and then I want to address Kyle's statement. First of all, Rachel, the dotted lines are there for our reference. They're for reference for us so that we do not cross them in regards to the vertical asymptote, and that we follow them as the end behavior to the left and to the right. I'm going to show you a different end behavior in a moment. I would suggest that when you draw them out, you do them. If you're doing like a multiple choice thing, then obviously they're not really necessary, but you should have them as a reference because they're very important. Matt, to address your statement. First of all, 2 + 2 = 4. No, you can't do math. Because 2 + 2 = 4, number one, only exists in your decimal math system. It does not exist in different versions of mathematics, because they do exist, different versions of mathematics. Second of all, 2 plus 2 equals 4 is much more complex than you make it out to be. You know that 2 plus 2 equals 4 because you learned that much earlier on, but can you definitively prove it? You could say that 2 apples plus 2 apples equals 4 apples, but you have not proven that 2 plus 2 equals 4. Can you abstractly prove that 2 plus 2 equals 4? Because mathematicians have actually done that. And it has taken many, many, many books to actually definitively prove the abstract nature of 2 plus 2 equals 4. You're just not looking at it from the right perspective. Now, Kyle, yes, anecdote time, because this actually addresses Matt's thing. No, you have not done a complex problem when you were 4 years old. You haven't. I'm talking about the abstract nature of it all. So you're not thinking of it from the right perspective. You're literally looking at it as if you were looking through a keyhole. I'm talking about if the door will actually open. I'm talking in a figurative sense. Mathematics is much more complex, Matt, than you think. The only thing that you are looking at in regards to mathematics is the tip of the iceberg. You only look at the tip of the iceberg. You are not looking at the massive amount of ice that is underneath the water that's actually supporting that tip. Yes, it would defeat the purpose of the keyhole, but here's the idea of the keyhole, Matt. There's a door, and it is locked. And you could only peek through the keyhole. Obviously, in today's world, it doesn't really exist. I'm talking about like hundreds of years ago where you could actually peek through keyholes. The door's locked. You can see what's inside, and you can only appreciate the limited scope that you can see. Mathematicians have been able to open that door, and they have been able to see what is on the other side and see the supporting structure that has built up the mathematical knowledge that you have today. And as a 4-year-old, you're able to do that basic mathematical problem because of the complex work that they have done leading up to today's world. No, they don't break and enter, Kyle. They don't break and enter. Let me give you just a kind of a basic, here's the anecdote, a basic general idea. Here's a little side note. How do we know they did it right, though? Well, mathematics can be definitively proven. They can be definitively proven. There are mathematical proofs that we can follow that prove for all numbers. And the proofs are a little bit strange here and there. Sometimes you can do proof by contradiction. Sometimes you can do proof by, not extrapolation, induction. There we go, proof by induction. Mathematics has to be proven 100% or not at all. Who came up with what? Who came up with what? Math or the proof behind it? I am interested in what he's going to say. Who came up with what? The whole proof thing. Mathematical logic is something that we have known forever. The logic behind things. For example, if I were to make a certain assumption and then that assumption led to a contradiction, then I can say that that original assumption is wrong and the opposite is true. Something like that. For example, I make a claim. Numbers are infinite. There is no largest number. How do I prove that? Assume there is a largest number. Then I can show that if I add 1, then I have shown that, well, my new number is greater than my assumption, which leads to a contradiction. Conclusion, my assumption is wrong. There is no largest number. That's a mathematical proof right there, a basic one. What is going on? I'm about to show an anecdote of something. So Kyle, for example, here's my anecdote. Do you all agree with this statement? Is something, again, geometry. Don't cringe. Don't say maybe. It's a Pythagorean triple. This is a Pythagorean triple. 3 squared plus 4 squared equals 5 squared. I want to come up with a slightly different one. Yeah, there we go. You could also say, that. It's a Pythagorean triple. I hope you do. So yeah, I just proved it right here where it's like 5 squared plus 12 squared is the same thing as 13 squared. Now, I can say in general, I can say that there are, or there exist, infinite triples A, B, and C, where A, B, and C are integers. Matt, it has nothing to do with changing your mind. It has everything to do with changing your perspective. But let me show you this. This is something, now again, Rachel, and they're going to throw up, but that's okay. But A squared plus B squared equals C squared. This is something that you guys have learned. This is something where there exists an infinite number of triples, A, B, and C, or A, comma, B, comma, C, where A, B, and C are integers. That has been shown. It's been proven. Now, here's the anecdote. Roughly 400 to 500 years ago, somebody looked at A squared plus B squared equals C squared, and they wondered, is there an integer solution? Is there an integer solution for this? When I say integer solution, again, I'm talking no decimals. Is there an integer solution for that? Furthermore, is there an integer solution A, B, C, for when you have an exponent that is greater than or equal to 3? There was a mathematician named Fermat, Fermat, and he saw this question in a mathematical textbook, and he wrote in the margins of that textbook that he had a solution, but the solution was too large to fit in the margins of this book. He had written all over the margins of the book, kind of making his little mathematical notes. So he had looked at something like this, and he wrote that in the margin of the book that he had a solution, but it's too big to fit into the margin. No one ever found his solution. And what people had pretty much done over the course of several hundred years was they tried to prove this statement. What Fermat had said was, there is no such solution. He says there's no solution. He said you can't do it. So for 450 some odd years, from the 1500s to today, that's my son actually, from the 1500s to today, no one could find a solution. Until there was a mathematician at Princeton University in 1993. He spent multiple years coming up with a proof to this particular problem. And he became world famous for a while. His name was Andrew Wiles. You can look him up. There is an amazing book about his journey in finding the proof to Fermat's last theorem. I believe it's called Fermat's Enigma. I have a copy of that book somewhere around here. It's an amazing book. The general idea behind mathematics: a mathematician needs to see what's behind that door. A mathematician needs to see what's on the other side of that door. They are not content with just looking through the keyhole. There is a hunger, there is a desire to have mathematical proof to prove a lot of the claims that we make. It is a certain mindset, an obsession that not a lot of people have. And for people to just simply blow it off like, why do all that work for such a simple solution? I ask you, why not? Why not? My wife used to call, or no, she still does actually, she calls it motivational math with Mr. Markey. I should do speeches because it's hard and annoying. Kyle, why bother going to the top of Mount Everest? Why bother trying to go to the moon? Why bother doing anything? That's all I got to say to that. Let's do another example. I'm going to wrap up with this today because I spent a lot of time on that anecdote. Final example today, and this is a non-basic problem. Non-basic problem. Kyle, why would you go to Mount Everest? Because it's there. Why not? Anyway, back to this. Ladies and gentlemen, last example I have for you today, and then I gotta close off this stream. After this example, of course, I have x cubed over x minus 1. Let's take a look at what the calculator says first. I think Matt kind of jumped out on my anecdote, unless he's still here, and he's trying to come up with a response. Is that a 3 or a 2? It's a 3. I'll rewrite it. There we go. X cubed divided by x minus 1. Let's take a look first. Who the heck knows? Look at that. What does that look like to you? What does that look like to you? To me, it looks like something that wanted to be a parabola and broke in the middle. It's amazing. This is amazing. Don't freak out, Kyle. It's amazing. So, let's go through this process. First and foremost, you can't factor. So don't worry about it. Since you can't factor, and since nothing simplifies, there are no holes. So I'll write can't simplify, no holes. Next, let's find a vertical asymptote. Vertical asymptote, you set the denominator equal to 0, and you solve. You have a vertical asymptote at x equals 1. Next, let's find a horizontal asymptote. You set the leading terms of the top and bottom of the fraction, and simplify. You end up with a curved asymptote. Again, this y equals x squared determines the end behavior of your graph. And I'll recap this in a moment. You can find an x-intercept by setting the numerator equal to 0 and solving. This would just only get you x equals 0. Let's recap exactly what the heck just happened. Don't be scared. Nothing can simplify. You can try to factor, you can't. But since you can't, no holes. Next, Take the denominator, set it equal to 0. You get a vertical asymptote. Next, take the leading terms from the top and the bottom of the fraction, simplify. You get the graph's end behavior. Unfortunately, it is not a horizontal asymptote. It is what they call a slant asymptote, or an oblique asymptote. Yes, it's safe to look at the problem, Kyle. Then, you could determine x-intercepts if you wanted to by taking the numerator and setting it equal to 0. Boom, done. Let's find a table of values. Find a table of values. So with this table of values, you can see right here, yes, there is your vertical asymptote. I'm going to find a few points to the left. All right. -1, 0.5, 0, 0, which I already knew 0, 0. Few points to the right. 2, 8, 3, and 13.5. It's very important that you recognize what this graph looks like before you begin doing anything, because you see the general shape that it has. Draw this graph out. May have to go up a bit higher here. There we go. First, let me put the vertical asymptote at 1. There's the vertical asymptote. Now, the horizontal asymptote, this is slanted. This actually describes the end behavior of this graph. The end behavior of this graph is going to look like a parabola. Let me show you something on the calculator. I think that'll do it. Watch very carefully. I changed the symbol for the second graph to just be this little dotty thing. Watch what happens. Look at that. Look at that. I'll do it again. Watch. Watch. It's going to graph it again. Here comes the first one. Here comes the second one. That circle is indicating what the end behavior, the far left to the far right, of what this graph is looking like. Yeah, he might have run away, or he might have just been kicked off. I don't know. He could be anywhere. That's okay. I don't think he liked my speech. But back to this. One more time, just to kind of show you, because I want to make a huge point about this. Here comes the first graph. Here comes the second graph. The second one is the end behavior. It's technically the asymptote. It's going to describe what the ends of this graph are going to look like. So, let's plot some points. -1 and 0.5, 0, 0. Now that doesn't really tell us much, but according to what we know about this, I know that this graph is going to follow going to the left, looking like the left side of a parabola. I know what this looks like based on what the calculator was able to show me. 2, 3, 4, 5, 6, 7, 8. There's 2, 8. 9, 10, 11, 12, 13 and a half. Right there. Now, again, this is terrible. But to the right, this thing is going to follow the rest of that parabola. And according to what the calculator showed me, and you can see that right over there where I'm pointing with my pen, I know that this graph is going to do that. This is a terrible looking graph. It is. But it follows the exact rules that we have put into place with these things. The domain is exactly the same. It's not as horrifying as you think, Kyle. The domain is exactly the same as it's always been, -infinity up to the asymptote, and then 1 to infinity. You don't have to worry about range with these things. Um, eh, just because it could be different from problem to problem. Why do these exist? They exist because they do. They exist because they do. I'm going to do one more problem with you guys, actually. I just got to find the right one. No, I'm going to come up with it on my own. Why do they exist? They exist just because they do. Nobody ever asked, why does calculus exist or mathematics exist in general? It just does. Mathematics exists outside of our minds. It exists outside of our minds. It's an abstract concept. It's amazing in reality. I want to do one more example. I want to make sure that I get this one right. Yes. It might be just you guys. For now, last example, non-basic. This should be my last example. Let's see. There we go. Let's see what the calculator says first. I'm looking at the calculator and graphing this thing out. Look at that wonderfulness. Look at that wonderfulness. I don't know. Let's see what happens. Again, last example, Kyle. I promise this is the last example. Let's go through this a piece at a time. Step 1. See if you can simplify anything. To see if you can simplify anything, you're going to need to factor. And if you factor, you end up with something like this. Nothing simplifies. No holes. Since nothing simplified, there's no holes, I'm going to move on to the next thing. Okay, next thing. Let's look for our vertical asymptote. Vertical asymptote. Set the denominator equal to 0. Well, if I do this, I get x equals 4 and x equals negative 3. I actually have 2 different vertical asymptotes. 2 different ones. Horizontal asymptote. You take the leading terms and divide them and simplify. Now, this is our basic rational function, which has a horizontal asymptote at y equals 0. You could do your x-intercepts, set the numerator equal to 0, and solve. You get negative 2. Why are you yelling? Kyle, don't be scared of math. Let me literally walk you through the exact same thing. It's the same thing over and over again. Step 1. See if you can simplify. Factor, nothing simplifies. Nothing simplified, no holes. Next, set the numerator. Set the bottom of the fraction, the denominator, equal to 0. Solve. You got your vertical asymptotes. Take the leading term of the top and the bottom, set them up in a fraction and simplify. You have your basic rational function, which means you have a horizontal asymptote of y equals 0. Set the numerator equal to 0. Solve. You get your x-intercept. Let's go for a table of values. Now again, for a table of values, you really only need a few points to the left and a few points to the right of where your asymptote actually is. Move this over a little bit. There we go. See that calculator screen a little bit better. Let's see. Negative 5, negative 0.17 it rounds to. Negative 4, negative 0.25. don't worry about putting the asymptote. -2, 0. -1, -0.1. All right. Scroll down a little bit. Let me go to the other asymptote. There we go. 2, -0.4. 3, -0.83. There's the other asymptote. 5.875. 6.44. You get that directly from the calculator. Let's graph it. See what it looks like, and I'll compare it to the calculator graph in a moment. Let's put our asymptotes. There is the vertical asymptote. There is the other vertical asymptote. This thing has 2 vertical asymptotes. Then you could put your horizontal. Now your horizontal is existing right at y equals 0. So you can just embellish it right on top. You could put your x-intercept, but it's one of the ordered pairs. So -5, -0.17, really tiny number. -4, -0.25. It's going to run down the vertical asymptote, and it's going to follow the end behavior to the left. All right. -2, 0. -1, -0.1. That's weird. 2, -0.4. It's about right there. And 3, negative. Oh, that's weird. That's really weird. Again, compare to what you see in the graph, ladies and gentlemen. Let me get rid of my axes here so you can show you a little bit better. Here comes the graph. Look at that. There's the first curve. There's the break for that middle curve. And then there's the last curve. You can kind of see that going on a little bit here, where it's curving downward and curving upward. Lastly, 5 and there, and 6 and a little bit lower. There we go. Whenever we do problems like this, you're going to have either the calculator, or if you're on a computer, you can use Desmos. Either one is acceptable. Either one is perfectly acceptable. Just make sure you're using it properly. Anyway, like I said, this afternoon I'm going to put timestamps in here so you can see these examples. Obviously, you have a minor due, but, you know, by the time most people watch this, that minor may already be passed. But there will be an assessment on graphing these things soon. So make sure that you're looking at the original video teaching this and these practice problems going through this process. All right. See you guys later.